Alright, so this problem is a little more tricky than it seems at first. We are asked to find the dew point if the humidity is 65% on the day where the temperature is 25 degrees Celsius. So what is the dew point? Dew point is when partial pressure, so I'll write it down at the same time as I say it here. The dew point is when partial pressure is equal to the saturated vapor pressure. But we also know that humidity, or relative humidity, is equal to partial pressure divided by saturated vapor pressure. So, from those two equations, we could conclude that dew point is when the humidity is 100%. Because in this equation there's a times 100% here if you want it in percentage. So if partial pressure is equal to saturated vapor pressure, then this cancels out, and what remains is 100% humidity. But it gets a little confusing now, because in the question we're asked what is the dew point if the humidity is 65%? So that doesn't really make sense. However, how we need to understand this question is, imagine a day where the temperature is 25 degrees Celsius and the humidity is 65%. So imagine a day like that. What would be the dew point in that day? So, in other words, if the humidity was 100%, what would the temperature be? Because dew point is a temperature, so we want a dew point in degrees Celsius. Alright, so let's get started. Humidity of 65%, we'll use this equation here. Humidity equals partial pressure divided by saturated vapor pressure times 100%. So humidity of 65% equals partial pressure. And now we'll have to look in a table to know what is the saturated vapor pressure if the temperature is 25 degrees Celsius. And this number is 3,170 Pascal, which is given like 3.17 times 10 to the 3. That's 3,000 times 100%. Alright, so now we want to isolate this variable, partial pressure. So what is the partial pressure on that day? So we can simply isolate it by taking the 3000 Pascal and the 100% and sending it to the other side of the equation. And so we end up with 6500 times 65% times 3070 Pascal divided by 100%. And this is equal to a partial pressure of 2061 Pascal. Good, so we have the partial pressure, but what we're asked is the dew point. So the dew point is the temperature at which the partial pressure is equal to the saturated vapor pressure. So since we know what the partial pressure is now, partial pressure is 2061 Pascal. This automatically gives us the saturated vapor pressure. It will be 2061 Pascal. And now we can go look at the table of saturated vapor pressures as a function of temperature and find which temperature corresponds to this saturated vapor pressure. So let's have a look. It is between, so if I'm looking at the, okay, so go with me, look at the table 13-3, saturated vapor pressure of water. I know you can't see it right now, but you could look in your manual, page 379. And if we look at the pressure column and try to find a pressure of 2000 in there, it would be right in between 15 degrees C and 20 degrees C. So my answer to this problem would be the dew point equals between 15 degrees Celsius and 20 degrees Celsius. And that would already be quite a challenging problem, I find. However, in the solution, the answer we're given is 18 degrees Celsius. So we were right. This is between 15 degrees Celsius and 20 degrees Celsius, but they managed to find a more precise answer. And I think what they did is they assumed that the table was linear. So let me explain here. In this table, we have 15 degrees C, 20 degrees C, and then we have a pressure of 1710 Pascal corresponding to 15 C, and a pressure of 2330 Pascal corresponding to a pressure of corresponding to a temperature of 20 C. And so what we could do is assume that the transition between those two temperatures will be linear in pressure. So let me draw this for you. If we have temperature in Celsius here and pressure in Pascal here, well, we can place those 2 points on this graph. 1520, 1710, 2330. We know those 2 points for sure are there. And what we found in the previous slide is that our saturated vapor pressure is 2061. So what we really want to know is to what temperature corresponds 2061. And there are many ways this could go from one point to another, right? It's not necessarily linear. But I think in this problem, what they do is they assume a linear relationship here between those 2 points. So that means that since it's linear, we can find an equation for it. Y equals mx plus b. And from this equation, we will be able to relate, let's try and do here, the pressure we found to the temperature we need. So there's a lot of work required to do that, but it's not very complicated. So just bear with me for a few extra minutes while we try to find the equation linking those 2 points, assuming it's linear. This is an assumption we have to make. There's nothing in the problem that says that it should be linear. But it's often the best thing we can do when we have 2 nearby points. We can just say, let's assume it's linear. The closer the 2 points are, the more likely this is to be correct. All right, so y equals mx plus b. We can find our slope, m. M is delta y divided by delta x. And so this will be, delta y will be 2330 minus 1710 divided by 20 minus 15. And so m is equal to 124. Then what we can do is rewrite this equation. Now we know that y equals 124 times x plus b. And now what we can do to find b is to replace x and y by one of those 2 points. So we'll do it with this point here. 1710 equals 124 times 15. This is not an x, this is just a multiplication sign. The x has been replaced by 15 plus b. And so if we isolate b, we calculate that b equals minus 150. All right, so final equation will be, I'm running out of space here. I can write down over here. The final equation will be y equals 124x minus 150. So this is the equation that we calculate for this line linking the 2 points. And now that we have this, we can put our value of y 261 into this equation and find the rated x. And so that would be 261 equals 124x minus 150. Oops, 150. And by isolating x in this equation, we find that x equals 17.8, or we can also approximate to 18 degrees Celsius as they did in the solutions. So I think that's what they did. This would make the most sense to me, and we get an answer that is very close to what is in the manual. Actually, if we round this off, we can obtain 18 degrees Celsius. All right, so thanks for staying with me for this rather long problem, but I think we got it right in the end. And so good job. Just keep up the good work.